We have another example here. In the figure shown, if A equals 1.0 centimeters, B is 3 centimeters, and I is 30 amps, what is the magnitude and direction of the magnetic field at point P? So in our picture, we have this kind of quarter circle section. It's only a portion of two coils, but they're connected, so the same current is flowing throughout all portions. So if we think of these individually, they would make up a whole loop individually if they were not connected in this particular manner. That's my attempt at drawing the loop. So the actual wire itself is 1/4 of a loop. Now the portions that have these straight edges, they are straight wires. But if we think about the magnetic field around a wire, if I put my thumb for this bottom one to the left, I point the thumb of my left hand to the left, my fingertips would point in up here and point out down here. The magnetic field will totally circle the wire, but it will not create a magnetic field over at point P. So it's creating a magnetic field. That magnetic field just does not pass through point P. So we don't need to worry about the magnetic field of these two straight portions. So if you think of a moving charge always created a magnetic field that circled it. It cannot create a magnetic field along the path that the charge is taking. So ultimately, to find the overall magnetic field at point P, we need to add the magnetic field for this inner portion of a loop and this outer portion. So the overall magnetic field at point P will be the field due to the curved segment 1 plus the field due to curved segment 2. And since these are a loop where we're at the center of the loop, B of the coil, where we only have one turn. So if we had a full coil, we would have mu naught Ni over 2R. We only have one loop, so this becomes mu naught I over 2R. And we actually don't even have a full loop. This segment only goes 1/4 of the way around a loop. So the B for our segment, that says segment, is going to be 1/4 of a whole loop. So if a whole loop of wire carrying current creates that magnetic field, and instead we only have 1/4 of that wire, then we only need 1/4 of that overall field. So our equation we're going to use is mu naught I over 8R. So segment 1, I'm going to find these individually, then add them together. The magnitude, mu naught is our constant, which I have the exact value memorized. So that's what I'm going to put in here. So mu naught times I, the current flowing through this wire is 30 amps. I'm not going to worry about how we're getting that big of a current. Divided by 8R. The R in our equation is the radius of the loop. So this inside loop has a radius A, so the 0.01 meters. So B1 plugging the numbers in. Four point 712. I'm going to keep a few decimal places since I'm not at a final answer. Times 10 to the negative 4. The units will be Teslas. That comes because mu naught has units of Teslas times meters over amps. The 30, the current is in amps, and then we are dividing by R, which is in meters. So the amps and the meters cancel. We end up getting just Teslas. Now to add B1 and B2 together, I know I don't have B2 yet, but I will need to know the direction of the magnetic field due to this inner segment. So we need to use the right-hand rule. Since this current is looping, it's curving, it's portion of a loop, I'm going to point the fingers of my right hand in the direction of that current. So for this inner loop, that is counterclockwise. So opposite the clock. When I do that, my thumb points towards me. That represents the direction of the magnetic field, specifically in the center of the loop. But point P is in the center. So this magnetic field points out of the screen towards me. Or if we use a traditional Cartesian coordinate system, it points in the positive z direction. Okay, let's find B2, the magnetic field due to the outer portion. So really the only difference is, well, in terms of magnitude, in terms of numbers we're plugging in, is the distance away. So the R. So we have 4 pi times 10 to the negative 7 again for mu naught. We have the same current. We just have a bigger distance. So the 0.03. We do want that in meters again for the same reason. Oops. For this one, I'm getting 1.5708 Teslas. Now the right-hand rule, since the outer loop is also a curved portion of an overall loop, if I put my fingers such that my fingertips are pointing clockwise in the direction of the current, my thumb points away from me or towards the screen. Towards screen. So this magnetic field points in to the screen. The overall magnetic field in the center, we're adding these together, but we have to account for out of the screen versus into the screen. If we consider, so I'm drawing in the top right corner, a typical Cartesian coordinate system where x would be to the right would be positive, towards the top of the screen would be positive y, then out of the screen would be the positive z direction. So out positive k hat for z, in negative k hat. We're going to take these two numbers times 10 to the negative 4 minus, oh, I missed my times 10 to the negative 4 right here for B2. I apologize for that. Didn't get that written down. And so both of these are the k-hats. The minus sign is in front of the number for the minus k-hat. So the 4.712 minus the 1.5708. We get, I'm going to round my answer because we're at a final answer. We get 3.1 times 10 to the negative 4 Teslas in the k-hat direction, or out of the screen. So just saying positive isn't enough. It has to be a positive k-hat where we have defined our coordinate system. Out of the screen is totally fine. That is a specific direction. But we do definitely need to account for the direction in adding these vectors together.